Hello, this video is going to cover the QEMU TM4C123GH6PM Emulator that we created for the end of our semester. So in this video we're going to cover the emulator structure and then the devices that we had to make specific. We only implemented the ones that the class uses most often. So there's only the GPIO, ADC, UART, and timers. In the future, more could be added if needed. So this is the emulator structure. It is composed of the main device is the NVIC Cortex M4 processor, which is built by QEMU. We don't do that. But alongside that, we have several copies of each of our main four devices that we talked about. There's multiple copies of them because the TIVA board has multiple copies of them. So we just filled out all of the ones that we had available. So starting with the GPIO device, basically it just acts like a pass-through device from inputs to outputs, and then has gating controls with like the port control and alternate function select. To do this, we created a named QGPIO pin group for each of the 8 data pins. We have pin 0 through pin 7 in both the inputs and the outputs. And then each of those group has 17 QGPIOs. There's going to be one for the just the standard function, one for the analog function, and then 16 for each of the port control, like alternate functions. And then there's one sysbus IRQ that we use to connect to the NVIC for each port. Now, so there's one of these GPIO devices for each port, so there's 6 in total. Moving on to the ADC device, it has 12 inputs for each of the AIN. These are connected to a specific output from the GPIO device, so that when a user configures the GPIO correctly, it will connect it to whatever is connected to, and it can get the AIN correctly. Currently, we only have one trigger implemented, the manual one that starts the sample sequence. And so it converts the voltage it reads from the AINs, which we just used the level of the QEMU IRQ, and then we measured it as millivolts. So it'll take that and convert it based on the ADC's setup into a digital value that can then be used by the student as though it were the real device. It stores its converted values in an internal memory that can be accessed by the user using the macros. It also has 4 sysbus IRQs, one for each of the sample sequences, just like the real ADC device. So alongside the ADC device, we have an analog test device. We used it to test and show the functionality of the ADC. It just has 2 variables. One is telling it which ADC or AIN to use or be connected to, and then the other is just the voltage measured in millivolts. When someone goes in and selects an AIN and then sets the voltage out, it'll send that signal across the QEMU IRQs, and then eventually it should reach the ADC device and be converted. It does go through the GPIO device, so to use it, you have to configure the GPIO pins as well. This is only available in the TM4 machine, not the Cybot, because the Cybot has will have other analog devices, such as the sensors, instead of a just generic test device. For developers, this lives at hex 4000-2000, which is unused by any other device. So if you need to use it, you can access the variables there. So moving on, a quick aside, we need to talk about QEMU timers. In QEMU, there's a virtual clock that is used for all of the devices. And then QEMU timers use that virtual clock and can convert between the clock cycles and then a real timestamp in nanoseconds. So anything that uses a regular timing or just needs to wait a certain amount of time to do something, we can use the timers to do that because they have a callback whenever the time is reached. So, we're going to use this for the timers and the UART, as well as the servo and Wi-Fi to use this. So the UART device uses the QEMU timers to send or read 1 bit at a time at the specified baud rate, which is specified by the IBRD and FBRD registers. We have separated the read and write timers so that they don't have to be in sync with each other. The read timer will only start when it gets a receive or a start bit, which is 0 on the input line, the RX line. And then the write timer, basically once the UART is turned on and TX is enabled in the control register, it will just start pumping out data. Most of the time it'll just send a 1 if there is no data to send, but once data starts, it'll send a properly framed UART frame. Next, we have the timer device. This is different than the QEMU timers. This is the actual timer in the TIVA board. And because of their complexity, we only bothered to emulate the PWM mode of the 16 and 32-bit timers. So it stores a Boolean to track the output signal state, and then can toggle that depending on when it needs. And we'll talk about how that works in a minute. It has 3 outputs, 2 for each of the timers. There's a timer A and timer B, and then 1 is the ADC trigger, which we don't actually connect to anything. And then it also has 1 sysbus IRQ for its interrupt. So timer value registers are a special case. Because of the way the timers work, you can't just get a time clock cycle. In the real board, the timers are basically just a register that counts up every cycle. But the way the timers work, they don't work like that. So we have to do some math to get the actual timer value whenever it's requested. So first, whenever the timer gets loaded its initial value, the load value, we will store the current time in nanoseconds in the device state. And then whenever the user requests a timer value register, we can measure the current time in nanoseconds and then compute the difference and then convert that difference into clock cycles. And then depending on the count direction, we can either return just the value if it's counting up from 0, or if it's counting down from the load value, we can take the load value minus the difference, and then that will give us the proper register value for the timer. So how does the PWM signal generation work? Well, so there's a few steps that we need to do, because again, normally it just counts down, and then if the match register ever equals the load register, it will toggle to 0. And then once it hits the countdown, the level 0, it'll just reset and go back to the load and set it back to 1. We can't just check each frame or each clock cycle. We could. It would probably be very inefficient. I'm not sure how QEMU handles a lot of timeouts. So instead, we just convert the match and load values into nanoseconds. Then whenever we're resetting or starting up the timer, it will compute load minus the match value. And that gives us this time window here. And so it'll time out. Once it times out, we know we need to toggle this to 0. And then we set up the next timer, which is just the match register time. And that'll tell us when to switch back to load minus match. So it just toggles between these 2 different timings over and over again based on the signal state. And then we also need to handle a few edge cases. So the most important edge case is when match is greater than load. In the real timer, again, the output only toggles when they are equal. So if the load is less than the match, then it just never equals and they never toggle. In our case, that would cause a negative value based on this math. We would get load minus match would be a negative value, and that would cause issues. So instead, we just convert the load. We have a special case where we just convert the load to nanoseconds, set the timer to time out that, and then skip the state switching step. So that is all of the information about the TM4 board itself. There's a lot more detail you can find on our document here, where we go over all of the devices. This video is covering this part, the TM4C board, which has the GPIO, ADC, UART timers. Next video is going to cover the Cybot implementation itself, which has the servo and the Wi-Fi module. Thank you for watching.